So we're going to look at techniques of derivatives. So how to go about finding the derivative without going through the formal definition where we have to look at the limit as h goes to 0 of our difference quotient. And so this is going to make our life so much easier when we have to go through problems and use derivatives to solve. So I just want to go back and remind you, we kind of looked at an example of this where I had given you equations, and I said, okay, without even taking the derivative, you guys should be able to know what the slope is and be able to tell me what the derivative of that function would equal. And so recall, we had one that was y equals a constant. And so let's say f of x is equal to some constant c. C equals a real number. A way to write that mathematically is the double vertical lines on that capital R. That represents the real numbers. Okay, so we have f of x equals c. If we go through the long way using the formal definition of derivatives, we would look at the limit here as h is going to 0 of f of x plus h minus f of x all over h. The problem is because our function is just a constant, there's no x in that equation, right? So when I look at over here, f of x plus h, I'm supposed to plug in this x plus h wherever I see an x in my function. Well, there's no x there, so I just get back my constant c. So this first piece is equal to c minus f of x. Well, minus f of x, subtracting off this function here is subtracting off c all over h. So c minus c in our numerator is 0 all over h. Well, let's simplify that before we go in and do direct substitution. Well, 0 over any number other than 0 is 0. And rules of limits, if we take a limit of a constant, remember that was just the constant itself. There's no h value in here to plug in 0. And so this is equal to 0. So we have our first rule of derivatives. If your function f of x is equal to some constant c, so c is contained, that kind of funky e means contained, it's in that set of the real numbers, then the derivative, remember notation, we put that f prime of x is equal to 0. So the derivative of a constant is 0. Oops. It keeps wanting to jump. There we go. So we're going to have some rules of derivatives. So just like limits, if we had sum of terms with our limits, we could break it down as the limit of each term and then add them together. Same thing with derivatives. So if we have some function and we have plus some constant in there, when we take the derivative of that constant, that term, it's just going to be 0. So the power rule is one that we're going to be using all the time. And so the power rule says if you have some function f of x, which is equal to x raised to the nth power, we have to say that n is a real number. So n is contained, or is in the set of real numbers. It's a real number. Then the derivative of f prime of x, or derivative of x, which is f prime of x, is equal to n times x raised to the n minus 1 power. So in words, so the derivative of x raised to the nth power equals the power times x raised to the n minus 1 power. So if we had f of x, for example, is equal to, let's just start easy, x squared. So by this rule, we basically take our power, we bring it down in front, and we subtract 1 from it. Just get rid of that now. So the derivative, I take my power, I bring it down front, x, and then I subtract 1 from it. So 2 minus 1. So this is equal to 2x. So if I had f of x is equal to x to the 5th power, so 5 is a real number, by this rule, I'm going to bring my power down front. And then I have x, and I'm going to subtract 1 from that power. So now I have a 5 minus a 1 power. So f prime of x is equal to 5x to the 4th. Well, what if it was f of x equals x raised to the 2/5 power? So same idea, 2/5 is still a real number. We're going to take our power, we're going to bring it down front. So we get f prime of x is equal to 2/5 x, and I'm going to subtract 1 from this power. So usually when I'm subtracting 1 from my power, if I have a fraction as my exponent, I would write that as a equivalent one with a common denominator. So this is the same thing as f prime of x is equal to 2/5 x. So this is really 2/5 minus 5/5. So we have 2/5 x raised to the 2/5 minus 5/5 is a negative 3/5. So a lot of times we don't like to have negative exponents in our numerator or in our denominator, and to rewrite them as positive exponents. Recall, if you had a negative exponent in the numerator, we could make it positive by bringing it down to the denominator. So in this case, we would have f prime of x is equal to 2 over 5. Bringing this down to the denominator, I'd have x now raised to a positive exponent 3/5. I'm going to leave it like that. Actually, I'm going to write it one other way, that these are all equivalent. So recall, we could rewrite rational exponents as radicals, or we could rewrite radicals as what was underneath the radical to a rational exponent. So recall, if you have x or any base, maybe b raised to the m divided by n power, we could rewrite this as a radical. What was in the denominator is what index, what root you're taking of your radical. So this is the nth root of b raised to the n. Sometimes it's easier first to take the root and then raise your base to the n, and those are equivalent. So just kind of review, this is 2 all over 5, the x to the 3/5. We're writing it as a radical, the index. This is the 5th root of x cubed. Okay, so those are all equivalent, all mean the exact same thing, just written a little differently. So we're going to go over one more rule, but I just mentioned to the class that that power rule here, if you wanted to see the derivation, the proof on how we get that power rule, I will go over that with my STEM calculus class and post that as a supplemental video under your class that you can watch if you wanted to. So I'm going to go over another rule, which is the constant times a function. So another rule of derivatives. So let's say let k be a constant, or be a real number. If g prime of x exists, then f of x, which is equal to some k times g of x, is and I probably should have said, wait, then the derivative of f of x equals k times g of x is f prime of x. Remember, we had different ways that we could write this. I could write this as df dx. That derivative is equal to k times the derivative of g of x, g prime of x. So just like we were taking limits before, if we had a limit of a constant times a function, we could take that constant out and then look at the limit of that function and then multiply it by the constant. So here, if we have some constant times a function, we can rewrite it as the constant times the derivative of that function. Okay. So for example, let's say we had f of x is equal to 2 times the square root of x. And I want to take the derivative of this. It says find f prime of x. So in this form, I can't find the derivative quite yet because this square root of x is not written as a power. So first thing that we want to do is we want to rewrite the square root of x. So that has an exponent. And so if you have a radical and the index is not shown, it's a 2, it's a square root. So recall, square root of x is x raised to the 1 over 2 power. So let's rewrite that. F of x, we can rewrite f of x is equal to 2 times this x raised to the 1/2 power. So technically, if I'm thinking of g of x is equal to the square root of x, which is equal to x to the 1/2, and I look at the derivative of that, so power rule, We bring our power down front. So bring 1/2 down front, x, and we're going to subtract 1 from our exponent. So I'm going to write my 1 to have a common denominator. So instead of 1, I'm going to write it as 2/2. So our derivative function is equal to 1/2 x to the negative 1/2 power. So if I go back in here and I replace that, I could have done that work in there. This is f of prime of x. The derivative of that is equal to our constant, which is 2, times the derivative of this x to the 1/2 power, which we found to be x to the, we found to be 1/2 times x to the negative 1/2 power. So notice that simplifies a little bit. I have a 2 in my numerator here times a 1/2, 2 in the denominator here. Those are going to cancel. And I forgot to write this as a negative 1/2 power. 1/2 power here, negative. So my derivative function is x to the negative 1/2 power. If I wanted to rewrite that to have a positive exponent, I could bring that down to the denominator. So this is 1 all over x to the 1/2 power. And rewrite it as a radical. F prime of x is equal to 1 over the square root of x. Sorry. So we can find derivatives if we had multiple terms. Basically, you're just going through and taking the derivative of each term. And that was another rule. So maybe we'll just write that rule down really quickly, and then we'll stop for there. Okay, so if f of x is equal to a sum of two functions, let's say u of x plus or minus v of x, and we're given that the derivative of u of x and the derivative of v of x exist, then the derivative of x, f of x, we can just take the derivative and sum or take the difference of each piece. So the derivative of u of x plus or minus the derivative of v of x. Sum or difference rule of derivatives. Okay, so we'll stop there. We may or may not do some more problems on Thursday. I might just spend the day reviewing. So questions on that?